The third section under Chapter 36 on interference and wave nature of light has to do with a single slit as opposed to the double slit. And here we can see again that we get the same type of effect. Let's imagine we have a single slit and we have light that comes through this slit like so. And if we divide that slit up into two parts, let's say it has a width W, from here to here, it's W, a width W, across there. And if we divide it into two parts, then this part will have a width of W over 2. And as the light goes from the top of this and compares to the top of this, then the next part of this will be in the same ratio as this part to this, and finally this bottom piece will interfere with this. How do these interfere? Remember, what I'm doing is I'm dividing this slit up into two parts, the upper part and the lower part. And I can say, well, the light that comes through this top part, I can let it interfere with the light that comes through the top part here, as though it's a double slit. Then do the same thing with each of these pieces compared to each of these pieces. Now, how does this work? If I look at this distance is going to be W over 2, and when that is equal to, this is W over 2, times the sine of the angle. When that is equal to the wavelength over 2, then in fact we're going to get destructive interference. Or if it's an integer multiple of lambda over 2, which would be 3/2 lambda over 2, and so forth. Let's just take this first one, so we can cancel the 2 out here and write that sine theta is going to be equal to lambda over W times an integer m in order to get destructive interference. Now, you can say, well, why do we divide it into 2? What if we divide it into 3 parts, 4 parts, 5? Then you get the same type of effect. So you still get the same equation when you do this, no matter how you divide the slit up. So this is how we get interference when it goes through a single slit. But going back now and thinking about this physically, when light comes along and it goes through a single slit, we get bright places here in the center, and then dimmer, brighter, dimmer, brighter, dimmer, brighter, and so forth. So it exhibits this wave nature of interference in constructive and destructive interference, even though we just have a single slit. Why? Because parts of this are interfering with other parts in a constructive or destructive way. Now, it turns out that if I'm trying to resolve two objects at some distance away using an aperture down here where the aperture distance is d, then there's an equation. How can I resolve these two objects as the light from both of these comes through here and interferes? I'm not going to derive that equation, but I'm going to tell you that the theta minimum out to the two objects is equal to approximately 1.22 times the wavelength divided by the distance across this slit. So when I look at it through a region D, I'm only able to resolve things that are approximately, and just for a moment, forget about the 1.22, that's about 1. So I'm only able to resolve in an angular sense when the wavelength is about equal to the distance D of the slit. So when I have a really narrow slit, if this is very small, then I can resolve, my resolution is different in terms of the wavelength. So I can compare that wavelength to see how well I can resolve things with a given lens or with a given aperture. Now, if I have a diffraction grating, that is something similar to this, But with the diffraction grating, I'm going to just draw it over here. By diffraction grating, I have thousands and thousands of lines in a very small region, and what happens is I get all the interference at a given angle as I'm going over here. So a diffraction grating is a way that's very effective, other than a prism, for breaking light up into its various colors, because the wavelengths interfere at different angles. So for example, I could actually take starlight out here and take the gases from that star, or from a chemical reaction where things are being burned or vaporized, and break that up into the various colors. And by looking at the spectra of those colors, I would be able, using the diffraction grating, I'd be able to identify which elements are in the gases of that star or in that element. It turns out that the diffraction grating equation, I'm going to just write it up here, sine theta is equal to m lambda over width. Over d, where d is the distance between two of those adjacent cuts, or the width or the slit separation. Now red is always going to be dispersed by the greatest angle and violet by the least in a diffraction grating. This is the equation for diffraction grating. This is the equation for resolution of two objects. And this is the equation for a single slit. Single slit equation, you'll notice how it's basically identical to the one for a diffraction grating. The only difference is the width of the slit compared to the distance across between two adjacent cuts in your diffraction grating. And this equation here is for the angle of resolution. So basically you're saying you can only resolve things with a aperture that's comparable to the wavelength, and you can't get any better than that. That finishes our chapter 36.